Welcome everyone to Techdaily.ai. This deep dive is sponsored by Stonefly, your trusted solution provider and advisor in enterprise storage, backup disaster recovery, hyper-converged VMware, Hyper-V, Proxmox cluster, AI servers, SA365, a turnkey security appliance, public and private cloud. Check out stonefly.com for more info. Today, we're taking a deep dive into, well, some really foundational elements of cloud computing, things that let businesses build robust, scalable, and secure digital footprints. We're talking virtual private clouds, VPCs, and the critical role of load balancing. It's really all about creating efficient, resilient, and, adaptive online environments for whatever the digital world throws at you.
Yeah, it's fascinating, isn't it, how these core concepts, often working behind the scenes, are just absolutely crucial for modern digital operations. They're the building blocks, really. They allow for everything from isolated, secure internal chats to handling massive fluctuating user traffic without skipping a beat. What really jumps out at you as we start this deep dive? Maybe thinking about their strategic importance.
For me, I think it's the fundamental shift they represent. Taking the huge shared resources of the public cloud and carving out your own highly controlled, secure space within it. It's almost like getting a private, custom-built mansion right in the middle of a bustling city. So yeah, let's unpack that a bit more. How exactly does a virtual private cloud deliver on that promise of isolation and control? When we talk about VPCs, what exactly are we creating, and how does this virtual private space stack up against the older ideas of, say, a public or a private cloud?
Okay, so a VPC is fundamentally a logically isolated virtual network environment, something you provision within a cloud provider's public cloud infrastructure. Think of it as having your very own completely private network segment, but it's hosted on the massive shared resources of a public cloud provider. Like if a public cloud is a sprawling apartment complex where lots of tenants share common facilities, a VPC is your specific lockdown apartment within that complex. You control who gets in, what goes in and out, how it's laid out, even though the building itself is shared.
Right, so it really seems to combine the best of both worlds. You get the immense scalability and resource pool of a public cloud. But with the critical data isolation and granular control you'd normally associate with a private cloud, that sounds less like just a benefit and more like a real paradigm shift for security.
Precisely. That isolation is a game changer. Your VPC network is completely separate from other tenants' networks, even within the same cloud provider. That dramatically reduces the attack surface, and you get the power to define really detailed security groups and access control lists, basically micro-segmenting your network. This lets you regulate traffic flow with real precision, maybe restricting access to certain IP addresses or even blocking traffic from whole countries for compliance. This kind of policy-defined perimeter, it's a massive lead for managing physical firewalls. It gives you amazing control and agility to prevent breaches and enforce rules.
And one key advantage that really jumps out at me is the elasticity you mentioned. VPCs are incredibly scalable, right? You can easily expand your network, add or remove compute instances, storage, other resources, pretty much on the fly as your needs change. That seems perfect for those unpredictable workloads where demand can just spike or dip dramatically.
Absolutely. And that flexibility goes deep into customization too.
Yeah.
You have the autonomy to define your own IP address ranges, set up custom subnets, configure complex routing tables. You can deploy VMs, databases, serverless functions, you name it, directly into your VPC. And managing all this from a single dashboard, it significantly eases infrastructure oversight. It frees up your IT teams. They can focus on innovation and core business goals instead of, wrestling with physical hardware limits.
Right.
It really empowers your teams for genuine agility.
Okay, VPCs sound pretty amazing, like the ideal solution for a lot of cloud challenges. But like any powerful tech, there must be potential downsides or complexities, right? What are some of those gotchas listeners should maybe watch out for?
Yeah, that brings up a critical point. VPCs aren't without their complexities. The initial setup, the ongoing configuration, and especially migrating existing stuff into a VPC, that can be technically demanding. You're managing components like subnets, routing tables, network ACLs, security groups. Understanding how they all interact and getting them configured just right takes significant expertise. For folks with less experience, this multi-layered network configuration can easily lead to misconfigurations. And those are often the root cause of frustrating connectivity issues. Troubleshooting can feel like navigating a maze, honestly, given all the potential points where something could go wrong.
And what about the cost? Can they get expensive, especially for smaller businesses? Are there hidden costs maybe beyond the advertised price?
Yes, costs can definitely add up. Beyond just paying for the resources you use, you'll see charges for data transfer, especially traffic leaving your VPC, that's egress traffic. Also, IP address usage can cost you. And then there's the significant expense of hiring and keeping people with the high-level expertise needed for design, deployment, and maintenance. But there are smart ways to manage this. Look for cloud providers with flexible, scalable pricing plans that really match your business needs. Prioritize vendors offering solid 24/7 tech support and maybe built-in monitoring and maintenance services. And most importantly, opt for customizable solutions where you really only pay for the specific resources and features you're actively using. Avoid that temptation to over-provision. Another concern I hear sometimes is the reliance on the public internet. I mean, what happens if your internet connection drops or if your VPC becomes a target for a sophisticated cyber attack? That's a very real operational risk. A disruption to your internet connection or an attack that gets past your network perimeter. That can lead to significant downtime, lost productivity, and potentially hit your revenue and reputation hard. So robust mitigation is crucial. This means implementing extra security layers like high availability VPN connections, maybe dedicated network links like AWS Direct Connect or Google Cloud Interconnect, and advanced firewall rules at multiple levels. You really need a multifaceted strategy to ensure business continuity, even when facing network outages or targeted cyber threats.
Okay, now let's maybe shift our focus a bit. Let's talk about another indispensable component for managing traffic and ensuring reliability within these cloud environments: load balancing. What is it fundamentally, and why has it become so central to modern cloud application design?
Right, load balancing. It's basically the process of intelligently distributing incoming user traffic across multiple instances of your applications or services. Imagine a popular restaurant with several chefs in the kitchen. If only one chef prepares all the meals, orders will back up fast. But if orders are distributed smartly among all available chefs, service is quick and efficient. Load balancing does exactly the same for your applications. It stops any single resource from getting overloaded, which drastically improves performance. It also enhances reliability by routing around failed servers, providing crucial fault tolerance. It's truly essential for almost any internet-facing application expecting more than just minimal traffic.
That analogy really paints a clear picture. But how do these traffic cops of the internet actually decide where to send each request? Is it just random, or are there more sophisticated methods?
Oh, definitely sophisticated algorithms. Broadly, they fall into two camps: static and dynamic. Static ones, like the simple round robin, just distribute workloads sequentially, first request to server 1, second to server 2, and so on, without checking server health or load. They're quick to set up, sure, but can be pretty inefficient if some servers are lagging or fail completely. Dynamic algorithms, though, are much smarter. They look at real-time metrics like server availability, current workload, maybe connection count, or even response times. They'll actively shift traffic to the least busy server or the one responding fastest for the best efficiency. This relies on constant server monitoring and health checks, which also enables automatic failover traffic gets instantly rerouted if a server slows down or fails.
And when we look at specific cloud platforms, Google Cloud's load balancing is known for being particularly robust, isn't it? What are some of its standout features that make it so powerful, maybe different from more traditional approaches?
Yeah, Google Cloud load balancing really stands out. It's built on some seriously high-performing, globally distributed tech things like maglev, Andromeda, Google front ends, and Envoy. Just briefly, maglev is their massive scale network load balancer. Think high throughput, low latency. Andromeda is their software-defined networking stack, giving flexibility. Google front ends, GFEs, handle the global proxying and serving. And Envoy is that popular open-source proxy often used in microservices. So key features coming from this foundation. Well, the single global Anycast IP address is huge. Traffic hits the closest Google point of presence and then routes over their private backbone to the nearest healthy backend. That gives you cross-region load balancing and automatic multi-region failover. It also offers seamless auto-scaling. It can handle massive traffic spikes, like 0 to full capacity in seconds, without needing pre-warming.
Pre-warming, right, where you have to manually scale up beforehand.
Exactly. Avoiding that is a big deal. And because it's entirely software-defined, you skip the physical hardware lock-in and managing individual load balancer boxes. It supports both Layer 4 TCP, UDP, ICMP, the network stuff, and Layer 7 HTTP, HTTPS for web traffic. And it offers both external, internet-facing access and internal private access.
So that global nature means users get directed to the closest healthy instance no matter where they are. That's a massive performance win. And you mentioned service tiers, too, affecting cost and performance.
Absolutely. The premium tier uses Google's global backbone. It means top performance and reach. The standard tier routes traffic over the public internet, which is more about cost optimization, usually fine for regional apps, which naturally raises an important question. With all these capabilities, how do you actually choose the right type of Google Cloud Load Balancer for your specific application?
Yeah, walk us through the main types. When would you pick one over another?
Okay, broadly, you've got application load balancers. These are for layer 7 HTTPS traffic. They act as proxies, they terminate the client connection, can inspect HTTP headers, then make a new connection to the backend. This allows for advanced stuff like routing based on URL paths, content-based switching, SSL offloading. They can be external or internal and operate globally, regionally, or in a classic mode. Then you have network load balancers for layer 4 traffic, TCP, UDP, other IP protocols. These come in two main flavors. Proxy network load balancers are also layer 4 reverse proxies. They mainly terminate TCP traffic for global distribution, offering similar benefits to application load balancers, but at the TCP level. On the other hand, pass-through network load balancers are layer 4 regional load balancers that don't proxy traffic. Instead, they preserve the client's original source IP address and use a technique called direct server return.
Direct server return.
Yeah, the response goes straight from the backend server back to the client, bypassing the load balancer on the return trip. This is useful for certain high-throughput scenarios or maybe legacy apps where keeping that client IP is critical, or for specific logging needs. They're built on that maglev and Andromeda foundation for really high performance.
Okay, so we figured out how to build our isolated VPCs and how to intelligently balance traffic within them. But what if your architecture grows? What if you need to securely connect two or more VPCs, maybe across different regions or for different teams, making them act like they're just one big network? That sounds like where VPC peering comes in.
Exactly. What's really fascinating about VPC peering is that it lets VPCs talk to each other using private IP addresses. It's basically creating a direct, low-latency network connection between two VPCs, making them behave as if they're on the same private network segment. And this brings some significant advantages. Enhanced security, because the traffic never hits the public internet, reducing exposure. Dramatically lower network latency, since you're routing directly over the cloud provider's internal backbone, not hopping across the internet. And often decreased costs, thanks to lower egress fees for data moving between peer networks. It's really fundamental for building robust multi-VPC or multi-region setups.
That sounds incredibly powerful for larger deployments, letting you create a truly unified cloud infrastructure. But connecting different networks, even virtual ones, well, it always seems to introduce its own complexities. What are some of the common pitfalls or troubleshooting headaches when setting up VPC peering?
You're absolutely right. There are definitely some common gotchas. A frequent one is firewall misconfigurations. Each VPC in the peering link needs explicit ingress and egress rules that specifically allow traffic to and from the other VPC's IP ranges. Getting the protocols and ports right is key. Overly tight rules here are a top cause of connection failures.
Okay, firewalls. What else?
Another layer to check is IP tables on your actual VMs or Kubernetes nodes. Even if your cloud firewalls are perfect, host-level firewalls on the machines themselves can block traffic from the peered network without you realizing it. And finally, always verify the VPC peering health checks in your cloud console. These built-in diagnostics are great. They can flag underlying routing problems, maybe overlapping IP ranges, or other subtle issues. They often provide crucial clues for troubleshooting.
And for organizations heavily into containerization, especially using something like Google Kubernetes Engine, I understand there are a couple of really important things they need to know to avoid major headaches with peering.
Absolutely. For peering to work smoothly, GKE clusters really need to be set up in VPC native network mode.
VPC in native mode.
Yeah, it's also called alias IP mode. Basically, it means pod IPs are treated more like native VPC IPs, using VPC routes and firewall rules. This hugely simplifies network management and makes integration with peered networks much cleaner. Without it, you're almost guaranteed to run into connectivity problems. Also, if you're using Calico network policies within GKE, for fine-grained pod security, you have to be careful. You need to review and configure your egress policies specifically to allow traffic to the peered VPC's IP ranges. Otherwise, Calico might just block that essential communication, even if your VPC peering and cloud firewalls are technically correct.
Okay, this brings us to something that often confuses people just starting out in cloud networking, the difference between a VPC and a VPN. They both have virtual private in their names, or implied. Can you clearly draw the line between their roles?
Yeah, that's a great question because while they both aim for secure networking, they serve fundamentally different purposes and operate at different layers, really. A VPC, remember, creates a logically isolated virtual network within a cloud provider's infrastructure. Its main job is to provide a secure, configurable environment where you deploy and manage your cloud-native stuff. It's all about building your private, secure playground inside the cloud, defining its internal layout and rules.
So VPC is about defining and controlling your isolated internal network within the cloud provider's hardware.
Exactly. A VPN, a virtual private network, on the other hand, establishes a secure, encrypted connection between two networks, usually over a public network like the internet. Its purpose is to securely extend your existing private network, maybe your office network, your on-premises data center, or even just a remote user's laptop to your cloud environment. It creates an encrypted tunnel for data while it's in transit, making the public internet behave like a private link for that specific connection.
Ah, okay. So the VPC is the secure environment you build in the cloud, and the VPN is the secure tunnel you create to or from the cloud, typically over the public internet. They sound like complementary tools then, often used together.
Precisely. You'd use a VPC for all your internal cloud communication services talking to each other, multi-region backends syncing up, maybe cloud-native Kubernetes networking. It keeps traffic entirely within the cloud provider's private network backbone. You'd use a VPN when you need to connect your on-premises network to your cloud VPC, or let your remote workforce securely access internal cloud systems, or transfer sensitive data that needs encryption in transit for compliance reasons. They're definitely complementary. You often deploy them together to bridge your private world and your public cloud resources securely and efficiently.
So wrapping this up, what does all this mean for you, our listener? Understanding these nuances, VPCs, load balancing, VPC peering it, isn't just about mastering technical jargon, is it? It's really about unlocking the true potential of building scalable, secure, and genuinely flexible cloud operations. These are the architectural decisions that underpin pretty much everything reliable and high-performing you interact with online today.
Yeah, by getting a deep grasp of these concepts, you really empower yourself. You can design resilient, high-performing network infrastructures that are ready for the, frankly, unpredictable demands of the digital world. It's about taking proactive control of your cloud environment, making sure your sensitive data is safe, and ensuring your applications stay consistently available and performant. That minimizes costly downtime and maximizes operational efficiency.
It really is a journey, isn't it? Continuous learning and optimization in the cloud. So, after diving deep into these core networking pieces today, what's maybe one aspect of your own current cloud infrastructure that this discussion makes you want to go explore or perhaps optimize further?
As you think about that, maybe consider how that interplay between network isolation provided by VPCs, intelligent traffic distribution from load balancing, and those seamless secure connections via peering, how that truly fortifies your entire digital presence. What does it really mean to build a cloud network where every component works in harmony? Not just for maximum efficiency today, but also to give you that peace of mind that your infrastructure is truly ready for whatever tomorrow brings, demands, and opportunities alike.